Welcome back to part 6, our grand finale on first-order logic. Over the past 5 videos, we have explored predicates, quantifiers, and inference rules. Today, we put it all to the test with a classic AI case study, the Wumpus world. Imagine a dark, dangerous cave where an AI agent must navigate using only logical deduction. Its mission? Find the hidden gold and escape alive. But the cave is treacherous, filled with bottomless pits, and a terrifying monster known as the Wumpus. To survive, agent cannot rely on luck. It must use a knowledge base, constantly processing sensory inputs to logically prove which squares are safe and which spell doom. Let's dive in. The Wumpus world is typically represented as a 4x4 grid. The agent starts in the bottom left corner at coordinate 1, 1. At each step, it receives a percept vector containing 5 elements: stench, breeze, glitter, bump, and scream. If the agent is in a square adjacent to the Wumpus, it perceives a stench. If it is next to a bottomless pit, it feels a breeze. If it steps on the gold, it sees a glitter. Moving into a wall produces a bump, and shooting the Wumpus produces a scream. First-order logic allows us to represent these transient experiences as formal predicates tied to time and space. Our agent's brain is its knowledge base, or KB. At time step 0, the KB contains the rules of the game. As the agent explores, it adds new sentences based on its percepts. For example, if there is no breeze or stench at square 1, 1, we assert not breeze at 1, 1, and not stench at 1, 1. We also know the agent is alive and in square 1, 1. By applying existential and universal quantifiers, we translate raw sensor data into grounded facts. Every single move expands this knowledge base, creating a growing web of logical truths that the agent uses to map out the unseen dangers of the cave. To make sense of these facts, the knowledge base needs general rules, formulated using first-order logic. Consider the relationship between pits and breezes. We can write a biconditional rule: for all squares x and I, there is a breeze in x. I if and only if there exists some adjacent square b that contains a pit. This is incredibly powerful, because it works in both directions. If the agent feels a breeze, it deduces that at least one adjacent square has a pit. Conversely, if it feels no breeze, it mathematically proves that all adjacent squares are absolutely safe. This logical equivalence is the engine of the agent's reasoning. Let's see inference in action. At start square 1, 1, the agent perceives nothing. Plugging not breeze at 1, 1 into our biconditional rule triggers a logical deduction. No adjacent squares contain pits. Using modus ponens and resolution, the agent updates its KB to mark squares 1, 2, and 2, 1 as guaranteed safe. The agent can now move to square 2, 1 without fear. This demonstrates the core loop of an intelligent logical agent. Perceive the environment, update the knowledge base, infer new hidden truths using first-order logic, and finally select a rational action based entirely on mathematically proven safety. But what happens when danger is detected? Suppose the agent moves to square 2, 1 and suddenly feels a breeze. The KB updates. Breeze at 2, 1 is true. The rule fires: a pit exists in an adjacent square. The adjacent squares are 1, 1, 2, 2, and 3, 1. We already know 1, 1 is safe. Therefore, the pit must be in 2, 2 or 3, 1. At this moment, first-order logic hits an interesting state: disjunction. The agent knows a pit is in one of those 2 squares, but cannot logically prove which one yet. To survive, it must retreat to a known safe square and explore a different path to gather more percepts. By exploring the alternative route, the agent eventually reaches square 1, 2 and detects a stench. This means the Wumpus is nearby. The adjacent squares are 1, 1, 1, 3, and 2, 2. Since 1, 1 is safe, the Wumpus is in 1, 3 or 2, 2. But remember the breeze at 2, 1. If the Wumpus were at 2, 2, the agent would have smelled a stench from 2, 1 as well, but it didn't. Using logical resolution, the agent eliminates 2, 2, leaving only 1, 3. The agent has deductively pinpointed the monster. It can fire its single arrow into square 1, 3, slay the Wumpus, clear the path, and safely secure the glittering gold. The Wumpus world perfectly illustrates the beauty of first-order logic in artificial intelligence. By combining a formal knowledge base with robust inference rules, an agent can navigate complex, hidden environments with mathematical certainty. We saw how universal quantifiers modeled the world's physics, and how resolution tackled disjunctive uncertainty. However, pure logic has limits. What if a cave has no guaranteed safe moves? That is where probabilistic reasoning takes over, which we will explore in future series. But for now, congratulations on mastering first-order logic. You have learned how to teach machines not just to calculate, but to truly reason.